what we want to look at here is a short demonstration of the RC circuit, and I forgot to put the ammeter in there, so there we go. So what we've got is a simulation here with a capacitor of 0.2 farads, or essentially 200,000 microfarads, but that's a really weird unit for that kind of capacitor. But so we've got a 0.2 farad capacitor. We have a resistor of 24 ohms, and we've set our battery to be 48 volts. Okay, so this is what we've got, and what I want you to notice, okay, what happens to the current when we flip the switch, right? So when we turn the switch on, you'll notice that right away, the immediate current in the system is very close to what Ohm's law would give for just a simple resistor battery circuit. It would be 48 volts divided by 24 ohms. Okay, 48 volts divided by 24 ohms, which would be 2 amps. Okay, and then you'll notice that the current's dropping, and it drops fairly rapidly at first, and then it starts to drop much more slowly over time. So let's watch. And there we go, we had almost 2 amps, and now it's down to almost an amp. And now you can see that the current is decreasing much more slowly, right? Why is that happening? Okay, why does the current behave this way? Well, it has to do with the interaction between the capacitor and the battery. Okay, so the capacitor and the battery are the two things that are mitigating all of this. So the battery wants to push the charge and wants to follow Ohm's law with the resistor, and it wants to push 2 amps through this circuit. But as the charge is gathering on the plates, as one of the plates becomes positively charged and the other plate becomes negatively charged, you can't draw as many charges off of one plate and put them on the other plate. There's fewer charges that can be drawn off because now the battery is kind of holding these plates constant as well. And so what happens with that is that means the current drops. And the current drops at a rate at which it is proportional to the amount of charge on the plates. Okay, so the rate at which the current is dropping is proportional to the amount of charge on the plates. The situation mathematically that gives rise to this phenomenon, or I should say, the equation that this phenomenon predicts, let's put it that way. The equation this phenomenon predicts is an exponential function. Okay, it's actually exponential decay. So what's happening is the current in the system is decaying exponentially. Okay, the current is in the system decayed exponentially, and that's what we saw. The system had a lot of current initially, and then it slowly died down after that. Let me see if I can discharge this resistor. And I don't know if the simulation will let me do that. Hey, it did. Cool. So now I have my system set up again just as it was originally, and we'll remove that. So now what we're going to do is we'll put the voltmeter across the capacitor. Okay, and right now there's 0 volts. And we'll put a voltmeter across the resistor. And right now there's 0 volts. Okay, but watch what happens when I flip the switch again. Okay, now keep your eye on the voltage. Since we already know what the current's going to do, keep your eye on the voltage. Now remember, voltage of the battery was 48 volts. So watch what value is initially across the resistor, and watch what value is initially across the capacitor. Okay, so now the voltage across the capacitor is growing while the voltage across the resistor is decreasing, right? And they're growing and decreasing at the same rate in step with each other. right? So what that is telling you is that the voltage across the capacitor is going to grow as the potential across the resistor decreases. And notice that their sum always was equal to the voltage of the battery. So what this is telling you is whatever voltage the battery is supplying, some of it is going to appear across the resistor and some of it is going to appear across the capacitor. Okay? And they will always add up to the voltage of the battery. Okay? So that is the first lesson. Right? And the reason these two numbers don't exactly agree is due to rounding. This goes out to 2 decimal places, this goes out to 3. Okay. But to within rounding error, the sums are 48. So let's see what's happening, right? So first things first, the voltage across the battery was constant. The voltage across the resistor was exponential decay. Okay. The voltage across the capacitor was growth. Now, the current through the circuit as a function of time was exponential decay, and it follows this form. Okay? I naught, where I naught is just from Ohm's law, the voltage of the battery divided by the resistor. I naught e to the negative t over RC. So RC is what's known as the time constant. Okay, and this is a measure of how fast this process or slow this process is going to occur. Okay, so the current follows this exponential decay law, but by Ohm's law, the potential through the resistor has to be the current times the resistance. So if the current is exponentially decaying, so is the potential across the resistor. So the potential across the resistor then follows the same exponential decay rule, where instead of the initial current, your initial value is now the voltage of the battery. Okay, so this is the potential across the resistor. But we have a rule called Kirchhoff's loop rule, which says that the potential across all of the components have to add up to that of the battery. So if I want to know how the potential across the capacitor is going to behave, the potential across the capacitor is going to be the potential of the battery minus the potential of the resistor. But the potential of the resistor is this. Okay? So if I factor out the voltage of the battery, I get this. Okay? And as such, what this is telling you is that the potential across the capacitor grows. So if I were to plot these, okay, if I plot my current as a function of time, my current's going to start out at some initial value and it will exponentially decay. And my voltage across the resistor will do the exact same thing. It is also exponential decay, and so it follows the same rule. So the current and the potential across the resistor effectively fall down to zero. They decay down to zero. Whereas the potential across the capacitor starts at zero. If I plug in 0 for t up here, then e to the negative 0 is 1. any number to the 0th power is 1. 1 minus 1 is 0. V naught minus 0 is 0. So this starts at 0, and then when I let t go to infinity, or a really long time, e to the negative infinity is close to 0. It's at infinity, it's technically 0. 1 minus 0 is 1. V naught times 1. So at really long times, Vc is a constant value which achieves the value of the battery. So this curve looks like this. That's not a very good sketch. Let me draw that one more time. So it will asymptotically approach the value of the battery while the current and the resistance asymptotically approach 0. Okay, so that is where this equation comes from. That is where the equation for the voltage across the resistor comes from. And in the next video, we will show you guys how to actually do something in Excel with this. Okay, so that'll be the next video. All right, stay tuned.